Dear students, after studying this module, you shall be able to know about principles of chromatography, types of chromatography, theoretical principles underlying chromatographic techniques, and qualitative and quantitative analysis by chromatography. The technique of chromatography is non-destructive in nature for resolving multi-component mixtures of minor, major and trace components into its individual fractions. Different variations may be applied to solids, liquids or gases. While chromatography may be applied both quantitatively and qualitatively, it is primarily a separation tool. However, final identification usually requires confirmation by some other analytical procedure such as infrared or IR spectroscopy, nuclear magnetic resonance or NMR spectroscopy or mass spectroscopy or MS. Quantitative analysis can be carried out by measuring the area of the chromatographic peak. Hence, chromatography can be used for qualitative and quantitative analysis. Chromatography is relatively a new technique which was first invented by botanist M. Sweat in the year 1906 in Warsaw. Sweat in that very year was successful in separating xanthophyll, chlorophyll and various other colored components through a column of calcium carbonate by percolating the extracts of vegetable. The column which Sweat used acted as an adsorbent and the various substances got adsorbed on different positions on the column. He termed the system of colored bands as chromatogram and the technique as chromatography based on the Greek words chroma meaning color and graphos meaning writing respectively. However, the term chromatography is a misnomer as in majority of the chromatographic procedures no colored products are obtained. Considerable advances have since been made and the method is used to separate colored as well as colorless substances. In Sweat's technique, the calcium carbonate column remains stationary and is hence known as the stationary phase, and the extract of vegetable that moves or flows through the column is hence called as the mobile phase. Thus, the chromatographic technique can also be considered as the separation method wherein separation of solutes take place between a stationary and a mobile phase. In 1930s, thin layer chromatography and ion exchange chromatography were introduced as separation techniques. Martin and Singe introduced partition and paper chromatography in 1941 and gas chromatography in 1952. During the next decade, the routine use of chromatography as a separation technique became universal and has been extended to several areas of study, especially chemistry, biology and medicine. Apart from its use in analysis, it is becoming a potential technique for purifying compounds in pharmaceutical industry and for production of pure chemicals. The recent spectacular developments in the field of biosciences are entirely due to chromatographic separation techniques of biomolecules. Chromatography is probably the most important single analytical technique used today and is likely to continue to be so in the foreseeable future. It is cornerstone of molecular analytical chemistry. Recently, its coupling with atomic absorption spectroscopy has extended its applications to elemental analysis. The information obtained from gas chromatography is particularly useful to the organic chemist or biochemist who wishes to know what materials he has synthesized in the laboratory or separated from living tissue as a part of his research assignment. In addition, it is valuable to the industrial scientist who wants to know the composition of his competitors' products as well as to other scientists involved in the characterization of matter. It can also be used as a method for preparing very pure compounds such as in the pharmaceutical industry or in the manufacture of pure chemicals. Now students, we will start with the definition of chromatography. Chromatography can be defined as the technique of separation of a mixture of component into its individual components by an equilibrium distribution between the two phases. The chromatographic technique is principally based on the differences in the rate by which the components in a mixture moves or flows through the porous medium, also known as the stationary phase, under the influence of some gas or solvent, also known as the mobile phase. In general, the chromatographic technique consists of several steps, including retention or adsorption of substance or substances on the stationary phase, separation of the adsorbed substances by the mobile phase, elution, the method in which the separated substances are recovered from the continuous flow of mobile phase, and qualitative and quantitative analysis of the eluted substances. Now, let us study about the types of chromatography. Chromatographic techniques are classified based on the type of stationary and mobile phase and used or chosen. The stationary phase may be a solid or a liquid, and the mobile phase may be a liquid or a gas. Separation occurs because of the combination of two or more factors such as rates of migration, capillary action and extent of adsorption, etc. In column adsorption chromatography, a liquid mobile phase is allowed to percolate down a solid stationary phase, generally packed in a vertical glass column. The stationary phase competes for the solute by adsorption, and the liquid mobile phase competes for the solute by dissolution. The method is termed as partition chromatography when both the phases are liquids. The two liquids are immiscible. Generally, partition chromatography is performed by coating the solid support with a liquid to be used as the stationary phase. Sometimes chemical bonds hold the liquid phase to the solid support. The liquid thus gets immobilized. Partition phenomena in this case are due to the differences in the solubilities of the solutes in the two liquids. In thin layer chromatography or TLC, the stationary phase is a thin layer of finely divided adsorbent solid spread over a glass plate. The mobile phase is liquid. In gas liquid chromatography or GLC, separation is achieved by partition between a mobile gas phase and a stationary liquid phase on solid support, packed in a column. Paper chromatography is essentially the same as column chromatography, except that the packed column is replaced by a filter paper strip. The mobile phase is a liquid. If the separation is carried out by allowing the liquid mobile phase to descend, the method is called as descending paper chromatography, and if the mobile phase is allowed to ascend, then the method is called as ascending paper chromatography. There are various types of chromatographic techniques, and some of them have been tabulated in this table as shown. In the very first column, we have shown the technique, the next column shows the stationary phase, and the third column shows the mobile phase. Starting with the first, we have liquid solid or adsorption chromatography as in HPLC, wherein the stationary phase is solid and the mobile phase is liquid. Next is liquid-liquid or partition chromatography, also known as LLC, wherein the stationary phase is liquid and the mobile phase is also liquid. In paper chromatography, the stationary phase used is solid and the mobile phase is also liquid. Next is thin layer chromatography or TLC, wherein the stationary phase can be solid and the mobile phase is liquid. Next is gas liquid chromatography or GLC, wherein the stationary phase is liquid and the mobile phase is gas. Next, moving on to gas solid chromatography or GSC, the stationary phase is solid and the mobile phase is a gas. Next is ion exchange chromatography. The stationary phase is solid and the mobile phase is liquid. Next is gel permeation chromatography or size exclusion chromatography, also known as GPC. In this, the stationary phase is a solid matrix and the mobile phase is liquid. The methods to be discussed in the following modules will be in terms of the terminology commonly employed and will come under one or the other of the categories listed in this table. A more recent development in liquid-liquid chromatography is countercurrent chromatography, which entirely eliminates the use of a solid matrix support. In another type, also called as the gel exclusion chromatography, the stationary phase is a porous gel and the separation takes place in accordance with the size of molecules in the gel. In affinity chromatography, or also known as bioaffinity chromatography, separations are done using gels modified to develop high specific biochemical reaction. Other modifications of this technique are metal chelate chromatography, ligand exchange chromatography, and dye-ligand affinity chromatography. The technique which makes use of all these principles and permits very rapid separation is high performance liquid chromatography, also known as HPLC. Now moving on to theoretical principles underlying chromatographic techniques. The basis of theoretical discussion in this module will be concerned with partition, adsorption and gas-liquid chromatography. With suitable modification, these concepts can be applied in the other types as well. The various types of chromatography is based on the distribution or partition coefficient, also known as Kd, that is used to describe the way by which a component distributes itself between two immiscible phases. For a compound distributing itself between equal volumes of two immiscible solvents, A and B, the value for this coefficient is a constant at a given temperature and is given by the expression wherein concentration in solvent A divided by concentration in solvent B is equals to Kd. The distribution of a compound can, however, is described not only in terms of its allocation between two solvents, but also by its distribution between any two phases, such as solid or liquid or gas-liquid phases. The term effective distribution coefficient is defined as the total amount as distinct from the concentration of substances present in one phase divided by the total amount present in other phase. Basically, all chromatographic systems consist of two phases. The stationary phase, which can be solid, gel, liquid or a solid with liquid immobilized onto it. The second phase, mobile phase, can be liquid or gaseous and flows over or through the stationary phase. The stationary and mobile phases are chosen in a way such as the components are separated based on the different distribution coefficient. This is obtained by setting up an adsorption equilibrium between a stationary solid and a mobile liquid phase, or the adsorption chromatography, partition equilibrium between a stationary liquid or semi-liquid and a mobile liquid phase, partition equilibrium between a stationary liquid and a mobile gaseous phase, ion exchange equilibrium between an ion exchange resin stationary phase and a mobile electrolyte phase, equilibrium between a liquid phase inside and outside a porous structure or molecular sieve, and equilibrium between a macromolecule and a small molecule for which it has high biological specificity and hence affinity. Chromatography columns are considered to consist of a number of imaginary closed zones, in each of which there is sufficient space for whole of the solute to attain absolute equilibrium between the mobile and stationary phase. Each zone is called a theoretical plate and its length in the column between two zones is called as the plate height, which has dimensions of length. The more efficient the column, the greater the number of theoretical plates that are involved and lesser is the plate height. The separations involved in chromatography can go in for one of two ways available. Column chromatography, wherein the stationary phase is packed onto a glass or metal column, and planar chromatography, where stationary phase is present on a planar surface like in TLC and paper chromatography. Both these modes of chromatography have their specific advantages, applications and method of operation. Now moving on to theories of chromatography. Two theories have been put forward regarding the rate of migration of solute and the development of peaks in the chromatogram. They are the plate theory and the rate theory or the kinetic theory. First is plate theory. According to the plate theory developed by Martin and Cinch, a chromatographic column consists of sieves of imaginary, discrete, yet continuous horizontal layers that are termed as theoretical plates. An equilibrium of solute among the stationary and mobile phases takes place at each of these plates. Migration of the solute is then assumed to occur by a series of its stepwise transfers between one plate to the other immediately below. The efficiency of partition in a chromatographic column gets increased as the number of theoretical plate increases. This is because the quantity of equilibrium will also correspondingly increase. Next is the rate theory. Rate theory explains the effect of variables, for example, the process of diffusion and mobile phase velocity, so as to describe the width of an elution band. It relates to the effects of these variables on the time taken by a solute to make its appearance at the end of the column. A molecule alternates rapidly between adsorbed and desorbed states. The time which the molecule spends in any one phase depends on the accidental energy gained by the molecule from its environment and is highly variable. A particle can migrate only if it is present in the mobile phase, and as a result the migration down the column is also highly irregular. Consequently, some solute molecules may migrate rapidly whereas others may lag behind. The net result of all these random individual processes is a symmetric distribution of velocities around the mean value, which represents the behavior of most common distribution of velocities or average particle. The width of zone gets increased as it migrates down the column because more time is needed for migration to take place. Hence, the zone width is directly related to the residence or retention time on the column and inversely proportional to the mobile phase velocity. Next, we will study about the zone shapes. Examination of a distinctive chromatogram reveals a similarity to normal error or Gaussian curves that are obtained when replicate values of a measurement are plotted as a function of the frequency of their occurrence. Such plots can be rationalized by assuming that the uncertainty associated with any single measurement is the summation of much larger number of small individually undetectable and random uncertainties, each of which may be positive or negative in sign. The most common occurrences are for these uncertainties to cancel one another, thus leading up to the mean value. With less likelihood, the summation may cause results that are greater or smaller than the mean. The consequence is a symmetric distribution of data around the mean value. In a related way, the typical Gaussian shape of a chromatogram can be attributed to the additive combination of the random motions of the solute particles in chromatographic band or zone. The breadth increases as the zone moves down the column because more time is allowed for spreading to occur. Thus, the zone breadth is directly related to residence time in the column and inversely related to the velocity at which the mobile phase flows. Next is standard deviation as a measure of zone breadth. The breadth of a Gaussian curve is of course related to the standard deviation. Approximately 96% of the area under such a curve is included within plus or minus 2 standard deviation of its maximum. Thus, a standard deviation derived from a chromatogram serves as a convenient quantitative measure of zone broadening. It is important to understand that the standard deviation for a chromatographic peak can be expressed in units of time or alternatively in distance along the length of the column. Thus, the standard deviation derived from the zone profiles would be in terms of length, usually in centimeters. More commonly, the abscisca of a chromatogram is in units of seconds or minutes, and a standard deviation derived from such a curve would carry units of time. Calculation of H and N from zone breadth. The broadening of a chromatographic zone is conveniently expressed as the square of the standard deviation, the variance per unit length of column, from which plate height and number of plates can be calculated. Next is sources of zone broadening. Chromatographic peaks are generally broadened by three kinetically controlled processes, that is eddy diffusion, longitudinal diffusion and non-equilibrium mass transfer. First, let us take up eddy diffusion. Zone broadening from eddy diffusion is the result of the multitude of pathways by which a molecule can find its way through a packed column. Next is longitudinal diffusion. Longitudinal diffusion results from the tendency of molecules to migrate from the concentrated center part of a band towards more dilute regions on either side. And last, non-equilibrium mass transfer. Chromatographic bands are also broadened because the flow of the mobile phase is ordinarily so rapid that true equilibrium between phases cannot be realized. The technique of chromatography is non-destructive in nature for resolving multi-component mixtures of minor, major and trace components into its individual fractions. Considerable advances have been made and the method is used to separate colored as well as colorless substances. Chromatography is probably the most important single analytical technique used today and is likely to continue to be so in the foreseeable future. A more recent development in liquid-liquid chromatography is countercurrent chromatography, which entirely eliminates the use of solid matrix support. The various types of chromatography is based on the distribution or partition coefficient, also termed as Kd, that is used to describe the way by which a component distributes itself between two immiscible phases. Chromatographic columns are considered to consist of a number of closest zones, in each of which there is sufficient space for the solute to attain absolute equilibrium between mobile and stationary phase. Chromatographic peaks are generally broadened by three kinetically controlled processes such as eddy diffusion, longitudinal diffusion and non-equilibrium mass transfer.